Okay, folks, let's continue our discussion about the average case, which is, well, actually the most challenging case about the quicksort. Okay, well, just now we finished the discussion about the best case and the worst case of the quicksort, and we know for the best case it is O n log n, and for the worst case it's O n squared. Okay, so for the average case, it's kind of easy for us to know it's gonna be somewhere in between the best case and the worst case. This means, well, for the average case, it will be somewhere between the O n log n and O n squared. Okay, and then how do we intuitively analyze that? And well, here is my idea. How about we suppose we have a bad partition every time. It's a bad partition, but it's not really the worst partition, okay? And well, let's just assume that for each partition, we are having a 90% to 10% partition. If we have this kind of partition all the time, and then I would say it is a pretty bad case, even though it's not the worst case. Okay, well, and for the average case, if we have random values and we are randomly picking the pivot, and then the case won't be as bad as always having 90 to 10% of the partition. Okay, and then if we always have the 90% to 10% partition, and what will be the Tn be? And then the Tn will be Tn equals 90% of the n, T 90% of the n, and plus T 10% of the n, and plus n itself. And by the way, what is that? That is for the partition itself, right? So for the partition algorithm, we always have the cos of the n. But in this case, I just want to make it easier, and I'm just assuming that the cos is just simply an n. Okay, so in this case, well, how do we draw the tree structure of the partition? Let's try that. Okay, let me go back to my drawing board again and say if we have a big chunk of the data to be sorted, and then say we have n values. Okay, and then for when we are doing the partition, there will be a pivot. And then say if we assume that this n value is really large, and then holding back this one value as a pivot doesn't really change anything. And then I can say, okay, so we have 10% of the n on one side, and then we have n multiplied by 90% on the other side. Even though we have 1 in the middle, it doesn't count anything because the n, the number of the values to be sorted, is really too big. And after that, okay, let's do another partition. So for another partition, if we have another p-value, and then, well, 10% on one side, so we only have 1% on one side, and then we have 9% on the other side, right? So that is for the partition of this one. And then how about this one? We have the pivot, and then we have 10% of the 90%, so that is the 9% on one side, and then we have the 90% of the 90% on the other side, so we have 81% of the n values. So if we just continue doing so, and we always assume that there are 90% of the values on one side, and if you want to see this tree structure, and you will see on the left side, well, eventually the problem size will be 1. And this will happen very quick because every time there will only be there will be only 10% of the value, another 10% of value, another 10% of the values, and eventually we will have the problem size to be 1, which is the base case, nothing to be sorted. We reach the base case very quick on one side. Okay, and how about the other side? So for the other side, we will have the 90% and then 81% and then probably 70-something% and then 60-something%. So this trail will be much longer, but guess what? if we continue doing the 90% on the right side, and eventually, after many more steps, we will reach the problem size to be 1, and this one, always the 90% from the top to the bottom, that is the longest trail possible from the original problem size all the way down to the base case, which is 1. Okay, so let me ask you this question. So we have 100% and 90%, or n. So for this one, let me write down as n multiplied by 0.9. And for this one, let me write it down as n multiplied by 0.9 squared. Okay, so if you go down and down, what will this be? This will be n multiplied by 0.9 with a k. Well, this k will be the length of this tree structure. So what will this k be? This k, let me see, this k will be, this k, how about I do this? 0.9 powers k will be 1 divided by n. Okay, and then how about we reverse that? So that will be 0.9 divided by 1, and then powers k will be the value of n. So for this value, instead of 1 divided by 0.9, how about I erase that? I change it to 10 divided by 9. Are you still okay? So we change it to 10 divided by 9. Okay, and then this will be easier. So now this k value will be the log 10 divided by 9 n. Okay, so what is the k value? The k value is how many steps we want to do the divide and conquer before we go from the n to the 90% of the n to the 81% of the n and all the way to the base case, which is 1. And then this is also the height of this recursion tree structure. Okay, so let's come back to the PowerPoint. Okay, so after we have this tree structure drawn, and then we will know for this tree structure, the height will be the log 10 divided by 9n. So this is the height of this tree. And then remember, for each time we do the divide and conquer, there is a partition, and the partition is a ON algorithm. Okay, so we are trying to do the ON algorithm up to how many times? Up to the log 10 divided by 9 n times. So if we multiply those two together, that is ON log 10 divided by 9 n. So this 10 divided by 9, this is base number, but this is also a constant, right? So this means if we want to ignore this 10 divided by 9 as a constant, and then for the 9 to 1 partition, this is a ON log n algorithm. And similarly, even if we are even worse, we are doing 99 to 1 partition all the time, this is still a ON log n algorithm. Okay, so now you have some feeling. So this means, well, for the random case or for the average case, well, it can't be as bad as 9 to 1 split or 99 to 1 split. However, we can see even we are doing 9 to 1 split constantly, or even if we are doing 99 to 1 split constantly, this is still a ON log n algorithm. What does this mean? This means for the average case, if we have to guess the average case of the quicksort, it should still be a ON log n time algorithm. Okay, so let's move on. Well, but if we want to do a formal analysis, well, a really rigorous, serious analysis of the average case, and then we have to consider all the possibilities. And for all the possibilities, I mean, well, this could be something very bad or it could be something very good. And well, for the real case scenario, we don't know. We don't know. It could be a 3% versus 97%, or it could be a 41% versus 59%. We don't know. But there is a probability. The probability is the chance will be equal that we have a 1% to 99%, or 2% to 98%, or 3% to 97%. Those possible partitions, the chances will be the same, and we want to consider all the possible chances, and so that we can do a really accurate analysis of the average case. Okay, so how do we do that? And the case will be, well, we want to consider all the possible partitions. It could be 0 to n minus 1. So why it is 0 to n minus 1? Well, that is the worst partition. For the worst partition, zero values on one side, and then n minus 1 on the other side. And what is the remaining one? The remaining one is a pivot. The pivot will stay there, right? So that is one of the possibility. And another possibility will be we have one value on the left side, and then we have the pivot, and then the rest of the n minus 2 on the other side. So that's another possibility. And then we have two values on the left side, one at the pivot, and then n minus 3 at on the right side. So those are all the possibilities. And the possibilities of those possible partitions will be the same. So we want to consider this case. And then how do we want to have the probability of which partition is likely to happen? And the answer is 1 divided by n, and n is how many values we are here to sort. Okay, and then so if we want to consider all those possible partitions, and then we have to add all the possible tn's together. So for the tn, it could for the tn now, well, if we only consider one of the partition, that will be tk on one side if we have k values on one side, and then t n minus 1 minus k, that is the value, how many values on the other side. However, for those k, this k can be any value from 0 to n minus 1. So we want to use sigma to add all the possible partitions together, and then remember for each of the partition, the probability will be 1 divided by n. Okay, and then what is the theta n? The theta n will be the cost of doing one partition. Okay, so this is really a hard recursion to solve because we don't know the k. We want to consider all the case, and then we also have to deal with this annoying sigma. So how do we do that? We can start to do some of the massage to make this case easier. So my observation is, well, since this k could be any value between 0 to n minus 1, and then for each of the possible tk, we count them twice. Okay, so what do I mean here? So we can have 0 to n minus 1 partition. We can have my n minus 1 to 0 partition. So for those two possible partitions, and then this means we are going to have the k as 0, so t 0 and t n minus 1 as one of the possible partition. And then on the other side, when k is n minus 1, and we have t n minus 1 and plus t 0 partition. And then for those two things, and we just count them twice. And if we see that, and then congratulations, we can save a lot of the trouble because we can extract these two here, and then we only have to deal with the tk, and we can get rid of this t n minus 1 and minus k. Okay, And then, well, this is a recursion we have to solve. It's a little bit easier, but still it's annoying. So we are going to use the induction here. Well, and at the very beginning of this course, and you hated induction, and now this is a perfect time to use the induction. Well, because for this induction, we want to prove that for the average case, the time complexity of the quicksort is still O in log n. And our process will be, number one, we want to guess the answer. And after we have the guess of the answer, we assume that, well, the induction holds, and then we substitute using a small value, and then we prove that for the value higher, this assumption also holds. Okay, so let's answer those 4 questions. So what's the possible answer of the time complexity of the average case? We talk about that. We say, okay, this is O in log n. Right? So in the next part, we want to assume that a inductive hypothesis holds. And what is the inductive hypothesis? And that will be, well, this Tn will be A in log n plus B. Okay, so we want to assume that this holds for some constant value of the A and B. And then we want to substitute the value with a smaller value, which is smaller than n. And let's just use the value of the k in this case. And eventually, the hard part, we want to prove that if for k, this holds, and then for a larger value of the n, this also holds. And this will be a full proof of the induction. So it sounds really easy, but right? So we just follow the standard layout of prove something using induction. Okay, but we are going to use this setup to prove the average case of the quicksort is also O in log n. Okay, and then we are going to start the fun part. Oh, I don't want to see that. Probably you want to say that too, okay? Well, I'm going to pause this video here and I'm going to continue doing all the mathematical things in the next lecture, okay? And well, I'm just giving you a quick idea of what you are going to see in the next class, okay? So, not fun, and I know it's not fun, but this is really a formal proof of the average case of the quicksort, and in a master course you have to see that. Okay, so I want to pause here. Well, I want to remind you that there will be homework 3, and homework 3 will be a coding homework, and then remember after this class, and you want to read the section 7.1 to 7.3 of this textbook, and there will be a even harder section 7.4. We will cover that in the next class. Okay, so that's it for today, and see you.